West Coast today via the miracle of modern technology. And I'm happy to introduce Dr. Adriana Kubasca, who's going to introduce the speaker.
Sure. So it's my pleasure to introduce Kiana Ehsani, the host, but Sina really made the connection. So Kiana has been working in the Prior Lab at the Allen Institute for AI. Prior standing for Perceptual Reasoning and Interaction, if I got this right. Before that, she did her PhD with Ali Farhadi, who I guess is now the CEO of Allen AI. I just found out recently. And she's interested in computer vision, machine learning, and embodied AI. And she can tell us about, I guess, domestic robots and other stuff. Thanks, Kiana.
Thank you for the introduction. Hi, everyone. Excited to see you all virtually today. I really wish I could be there in the beautiful Pittsburgh with the best restaurants in the world. I really love Pittsburgh, but unfortunately, I'm remote today. I'm calling in from Seattle. Yeah, very excited to be here. A little bit of introduction about myself. I'm Kiana. I did my PhD at University of Washington. I did my PhD mostly in computer vision, and towards the end of the PhD, I got more interested in learning visual representations from interaction. And the more I got involved with interaction, the more I realized that there is this need for embodiment when we talk about perception. So that's why I'm talking to you today about home robots. And my ultimate goal is to bring the perception into these embodied agents and give them the ability to see and act on that. So with that being said, as the title says, our goal is to bring the robots from simulation to the real world. And today I'm going to talk about three aspects that we've been considering. It's imitation, generalization, and personalization. Now, before I go deeper into talking about what exactly we have talked about, let me just give you a high-level idea of what I mean when I say embodied AI or robotics, because there are a variety of different definitions that these terms have. So I don't think there is anyone in this room that would not love to have a robot in their house. And we are all interested in bringing these robots into our homes, let them do our chores, but we're not there yet. So if you think about it, vision made amazing progress with large-scale data sets and benchmarks such as ImageNet. And LLMs showed a great impact by training on large-scale web data. But there are two things. One, all these models are all about talk and not action. And second of all, we haven't had that moment for robotics yet. So that's why my focus is to build generally capable agents with three characteristics. One, I want them to be mobile. There is a big line of work interested in tabletop manipulation. That is amazing, but my interest is for robots that can navigate and explore in the environments and are mobile and can be conditioned on natural language. So what do I mean by this is we want to go further away from having robots that will only use templated language. We want them to use just any natural language words. And the third part is I want these robots to be dexterous. I want them to do complicated, complex tasks in my everyday house. Okay. So now that we know what we want, what do we need for this? I would like to argue today that there are three main components that we need to build these agents. So this is basically ML 101. We need large-scale data similar to computer vision and large language models. We need a model architecture that works on a variety of tasks, and it can support complex tasks and environments. And more importantly, we need policies that can adapt to different scenarios and specialize to different needs of users. Basically, as soon as you try to bring the robots outside the lab environment, the one policy fits all paradigm is not satisfactory. Okay, so let me elaborate. This will basically show the structure of my talk. First, I'm going to talk about how we came up with a new approach to collect large-scale data in a way that is cheap, it's safe, there's no robot involved in the data collection, and is scalable. Second, I will talk about how I think we need a shift in how we think about navigation and manipulation of the robots, how the community has been thinking about these modules, and why and how we think we should combine these and look at these two components together. And then last but not least, I would like to talk about how we can deploy these models on real robots and get the policies that are adaptable to individual users. Okay, so let's dive in more details, shall we? So imitation learning for robotics, I'm not sure how many of the people in the audience are familiar with this line of research, but it was shown by a variety of different works that for manipulation, imitation learning works. One of these works was by Google, RT1, and they showed promising first results. Now, I would like to read a sentence from their paper. This model is trained on a large-scale real-world robotics dataset of 130K episodes that cover 700 tasks, collected using 13 robots over 17 months. So unless you are working at Google, collecting this amount of data for none of the academic labs or even like for many of the industry labs, it's not really possible and it's not scalable. So it required a lot of resources to collect this data. On another side, more recently, another work came out that the community had basically joined forces to have this great effort to address the data limitation. So it's called RTX, and it's from 21 different institutions, and they collected these data set of robot manipulation that works with a variety of different environments, and basically like collected the data from a variety of different environments and for a variety of different embodiments. But there are still some shortcomings. This is a great effort, but it's still mainly focused on manipulation only, so only tabletop manipulation. And I would like to argue that navigating the chaotic real-world houses is not trivial. And collecting that much data is impossible that will generalize to novel environments. So what is the solution? So here's the goal we have. Let's just imagine that we could have a simulated environment, that we could collect tons of these shortest path trajectories. It's simulation, so I have the information of where the agent is, where are the occlusions, where are the collisions, where are the objects. So I can calculate the shortest path and basically come up with these heuristic planners that take the agent from the initial place to the ultimate goal. So this is what we think the data would look like. You will have some egocentric videos of your agent moving around, and you'll have some actions corresponding to each frame. And for each task, you basically collect this data set. But there are a variety of different works in the community that has shown this type of data collection does not scale to the real world. Okay, buckle up because I'm going to have a little bit of spoiler. But because I want to make sure you are all sold on this idea before listening to all the details of this work, I would like to say it was possible. So the goal was to make agents that can navigate and manipulate objects in the real world. As you can see, this is the, can you see my mouse? Oh, yes, now you can. Okay. So this is a very big, huge house, and the robot is basically able to start from one room, go and explore and find the target object or manipulate the objects and pick up the objects that we want. Now, with that being said, let me start with a really big claim, which is also our paper title, and that is imitating shortest path in simulation enables effective navigation and manipulation in the real world. This is very unintuitive because in simulation, when we are generating these shortest paths, we have full observability. But in the real world, we don't have access to any of those privileged knowledge that we were using in simulation. So even for us, it was a surprising fact, but this is how we claim we can all solve a lot of different problems in robotics. Okay, so there are three components. There are the data, model, and how we transfer to the real world. And we basically had this hypothesis that if we gather expert trajectory from the simulation and train a supervised model on this data at scale, it can transfer to the real world. Okay. Now let's talk about each component that I just showed you one by one and basically explain how we made this work. Okay. The first question is, why do we think this would work? Because usually simulated environments are visually very different from real world. And then also, if you have a small set of scenes that are designed, they will not scale. In fact, just I think it was about 6 months before we put this work out, that another work came out that showed that training on shortest path in simulation will not result in generalization to the real world. What were they doing? It was a smaller set of manually designed scenes. But how we did it is we have two components, two works at AI2 that allowed us to scale these environments, simulated environments, to an unlimited amount. So we have Proctor, which is we have the capability of procedurally generate these houses that have, as you can see, they have a variety of different rooms, layouts, object configuration, and then we have Observers, which is this universe of 10 million plus 3D objects. So if we combine these together and put the Observers assets in these scenes, we basically get infinite number of scenes. And having the ability to procedurally generate these environments enabled us to make this work. Okay. So let's say that we have these environments. We still need a variety of different tasks. We need planners. So this is how we thought about this. We need a couple of different behaviors. Let's say object nav. So for those of you who are not familiar with the term object nav, it's basically short for object goal navigation, where the agent receives a target type of the object, and the goal is to navigate to that target object. Now, you can go with like templated object type, which is a task that is very popular in the community, but we were not satisfied with that. We want to have a variety of different specification. So it can be goal specifications such just by type. It can be by affordance. So for example, navigate to a container that can best be used for carrying tools to different locations. It can be by instance. For example, navigate to that yellow rectangular closed toolbox. So not any toolbox, but the toolbox that has the specific specification. And then local ref, navigate to the container that is nearest to the television. And so there are a variety of different goal specification that we can provide. And there are a variety of different behavior that we would expect our agents to do in the real world. We want them to be able to pick up objects if they're close to it. We want them to fetch the object. So explore the room find the object and then pick it up. And fetch to surface, for example, is find the basket shaped like cylinder and clutch it and put it on the bed. And we also added additional types of tasks, for example, additional navigation, exploration, complex rearrangement, and all that. Now, in order to basically narrow down, we have these simulated environment, and we have the benchmarks, tasks, and planners for all of these tasks. But for this work, this CVPR paper, we basically narrowed it down to a smaller set of tasks so that we can quickly evaluate all of our methods. And we chose these tasks such that there are some specific skills that is needed for each of those tasks so that we can demonstrate how well these skills can be learned from this data that we have collected. So just to give you a little bit of data that we use for this specific project, as I said before, we can generate unlimited number of trajectories, houses, and everything. We limited this, so the numbers that you're going to see in this slides is generated by 100,000 trained houses and 50,000 evaluation houses, trained on 10 million trajectories, and which is basically roughly equivalent to 110 million frames. And we have 2,000 evaluation episodes. So for each number that I show you today, they are on 2,000 evaluation episodes. This is one of the reasons why we believe in simulation. In real world, you can't go above 200 trajectories. And if you want to compare your method with a baseline, 400 trajectories, that takes a really long time. And we believe in evaluating our models in real world, but evaluating them in simulation allows us much faster turnaround time, much faster evaluation of our methods. Okay, so this is how our training data looks like. We are in the process of releasing it, and we will soon release this data. So we have a large scale data set of these expert trajectories. They have RGB observations with the corresponding actions. And we have 2 cameras on the robot because the axis, we use stretch robot, and the axis that the robot navigates is perpendicular to the axis that it can manipulate the objects. So that's why we have a navigation camera and a manipulation camera. And as you saw in this small video, we basically have a task for each trajectory, and each trajectory is basically an MP4 video of egocentric observation, and then we have action corresponding to each step. So we have the data. What do we need? We need a model. So at every time step, we input a language goal description as well as our camera frames. So we have 2 cameras, a navigation camera and a manipulation camera. And the goals and observations are encoded using pre-trained image and language encoders. We tried a variety of different image encoders and language encoders to show the capabilities of different ones. But the beauty of this is because we are freezing the encoders, you can, if tomorrow an image encoder comes out that is much better, you can just plug and play it. Then visual observations are basically embedded condition on the goal using a fusion transformer. And we just combine the visual observations with the temporal position encoding and other sensors, which we have a variety of different sensors. But for main experiments, we only input the previous action. Basically, you just want the robot to know what were the previous actions that it has taken. And we just combine all of the visual observations across different time steps. And finally, we have a causal transformer that predicts action at each time, condition on the previous observations and the goal description. So now there is a challenge here. Because we are doing mobile manipulation, the trajectories are very long. It can be up to 1,000 steps. This is not a problem that usually when people are working with tabletop manipulation have, but you need to have access to all the trajectories. So how are we going to train this? Because if we want to fit everything in memory, we won't be able to fit all of that. So we train on randomly selected sliding windows with temporal position encoding that gets randomized. So at each training step, we randomly just pick a sliding window of the trajectories, and we input that to the model and try to predict the actions in a supervised manner. But then when we are doing this during the inference time, we use the entire history during evaluation. The other training challenge is the expansion of visual vocabulary. So as a result, we basically pre-trained our model on static internet data sets, which have like thousands of objects and attributes to expand the visual vocabulary. So basically, this is why we are using the pre-trained image encoder or text encoders. Okay, let's look at some results. So I would like to show you the findings before I go into specific results, because I think the findings are the most important thing that might work in any, like might help a project of one of the people in this room. Finding number 1, exploration emerges from imitating shortest path at scale. This is very counterintuitive. Why would a model learn to explore if we are only training it on shortest path? The idea is when we bring this to scale, and because we have environments that are very big, the agents basically learn these sub-skills from the expert trajectories that they have seen. So the expert trajectories, even though they don't have exploration, even though they know exactly where the target object is and they go directly to it, along the process, because we're doing this at scale, they have seen how an agent moves from one room to the other. So they learn how to go between different rooms. They learn that they should never visit one room twice. They learn how to, if they see the object, they should go directly to it and issue a done action. Because we believe that the policies have to be able to determine whether they have finished the task or not. So this is our first and main finding that was very surprising to both us and the community. We don't do any RL, reinforcement learning, we don't collect any human data, and scale is the biggest factor here. Our model only uses RGB observation. It is very common in the community to use depth sensor, use LiDAR sensor, use different mapping functions, use some privileged information such as works that use with point nav, for example, like compass, but we only use RGB. And this is a very big finding because many people in the community believe that you need all these sensors in order to perform this task, but RGB is enough. Why this is important? Because robotics has been limited to these very low quality depth sensors. They've been limited to the noise in the LiDAR sensor, but we have the RGB cameras out there. They're amazing. So it's really nice to see that we can only perform this task with RGB. The next one is Spock is only trained in simulation. We don't do any sim to real adaptation. We don't do any real world fine tuning. And then finally, you're able to do long horizon tasks, including both navigation and manipulation, which I'm going to show you some results. Okay, so this is, for example, a training trajectory. This is shortest path. So the agent needs exactly where the object is, and it goes directly to it. During evaluation, all the agent has access to is the RGB egocentric observation. So it doesn't know where the object is. It doesn't know like what the layout looks like. But look at these trajectories. It's able to backtrack. It's able to explore these environments. And this was one of the most surprising behaviors that we saw that emerging from this model. The next one is the model learns to have a spatial understanding. So the goal here is to navigate to the highest fruit in the kitchen And there are some fruits here that are basically some apple, and there are some fruits here, banana. So the agent learns to go and check out all these fruits, and it is able to successfully determine which one is higher. So that's a very capable agent to be able to have this spatial understanding. The next one is the agent learns task-specific behaviors. That's fascinating. We tell it, locate a computer on a sofa. Finding a computer, which is a smaller object, is harder than finding a sofa. So you can see how in the beginning of the episode, it goes to this black grayish sofa, and it explores on the sofa, realizes that the computer is not there, continues backtracking and exploring the environment. It sees the next sofa and finds the target object. Okay. Now the real world. This is the part that we are the most proud of. We have this robotic lab at AI2, which is a five-room house, which, as you can see, it looks like an actual apartment, but it's a very big house. And the fact that the agent is able to go from one side of the house all the way to the other to find these objects is very impressive. It is also able to, again, similar to the ones that we saw in simulation, backtrack and go and pick up the objects. And it can also recover from mistakes. So as you can see on the top right trajectory, it starts, it tries to pick up the object, but it fails. So it knows how to retry, which is something that usually we don't see with the modular approaches. Okay, so making this work wasn't super straightforward. There were a lot of decisions that we have to make to change the final outcome. Since they might apply to your work, I thought it would be interesting to talk about these technical details to have a basically learning opportunity. So how important is the number of houses? Going from 100 to 10,000 brought about more than 10% improvement of the success rate. So that shows that the scale of the houses is very important. Next question is, what is the impact of number of training episodes? You can see how the more the number of trajectories, the more success rate you get. So this is a big selling point for why we need to use simulation, and just limiting ourselves to real world is not scalable. And let me just emphasize one more time that all the real world videos that you saw today, they were true zero shot, because those scenarios, those houses, those objects have never been seen in training, because we've been only training in simulation. How about the context window size? As expected, the context window size, the higher it is, the better the performance is. However, it's good to see that still, even with a smaller window size that we can fit in a normal GPU machine, we can still train this model as well. The last point is, actually this is not the last one, but one of the other finding was it is really important which image encoder to use. So CLIP, we know it's a very good visual representation, but we saw that the newer visual representations, visual encodings such as Dino and Ciclet performed much better. That is just telling us as the image encoders improve, we will be able to just use the same data and get better performance. And then the impact of transformer architecture. So we compared ourselves with just using a normal GRU, which is a common practice in embodied AI, especially people from more of the vision community. And we saw that we gained some improvement by using the transformers. So the question is, what if perception was perfect? Just for the sake of it, let's say tomorrow we have this visual representation that perfectly encodes the semantic meanings of each image. How well would our method perform? So the ones that you see in orange are the ones that are the numbers that we got by training on ground truth object detection and evaluating with ground truth object detection. So there is a big, the object nav is basically solved. It goes all the way to 85%. So that is just telling us that if we could get the perfect object perception, this is what the results would be. And the last one is Spock in the real world. So we have two separate types of experiments. One, we use a detection model and one without. But the numbers that I'm showing you here is to show you the sim to real gap. So the lighter green, this one, is, or the darker green is when we train our model with ground truth object detection. And the light green is when we evaluate our model in the real world with DETIC, which is an object detection model. So you can see that other than for pickup, all the tasks are getting relatively similar results compared to the simulation one. The reason why the pickup numbers are lower is when we designed the task of pickup, we assume that the agent doesn't need to move its body to pick up the object. However, in the real world, perfectly aligning the agent with the object is not really possible, and that's why we see a drop in the performance. Okay, before I go to the next phase of this project or this presentation, do we have any questions? Cool. Okay, so
Turns out, let's see. Go ahead.
Hi, I have a question regarding how the two data sets, the synthetic one and the real one, how similar are these two? And is there any requirement to?
Sorry, can I ask you to come closer to
Yeah.
the computer because I can't really hear you.
Or Adriana, you can repeat.
I can. It sounds like it may be a longer question. You can
Okay.
try. Why don't you? Yeah. Why don't you?
Hi, Kiana. I have a question regarding the similarity of the two data sets. How similar are the synthetic one and the real one? And is it a requirement to make your model succeed?
Which real data set?
I mean, it seems that you trained on a synthetic one and then tested on a real one, right? I mean,
Yes.
how far away are these two data sets?
Oh, very far. So our simulation environment that we are training on, it's all, I can go back to, let's see, show you the training trajectories. They are these synthetic rooms that the layout it's very different. And the objects are obviously very different because they are all simulation. Look at this. Okay. So this is basically what the agent sees. And the environments, because they're procedurally generated, they sometimes don't make that much sense in a sense that like you will have a bed, like a bathroom that opens to a kitchen. And the objects it's not photorealistic at all. But then this is what the agent sees. Let me show you. This is what the agent sees in real world.
Yeah, I mean, if we have like more similar training and testing, would we have better performance?
For sure, for sure. It's just a matter of how do we get that high quality simulation that resembles the real world.
Yeah, maybe the Sora can help.
Sorry, the what?
Sora, the newly come out.
AI, video
Oh,
generation.
Sora. Yes,
Yeah.
that's actually very interesting. I would
Okay.
love to see how physically realistic it is, but yes.
Joey, did you have a question?
Just real quick, what's the intermediate, is there any intermediate supervision?
Is there any intermediate supervision? I don't
No.
know if I know what that means. But
No, this is just all end-to-end training. The only supervision is the loss during training is the loss on the action. So basically the model predicts an action and we just had a loss on that.
It seems we have a lot of questions. Is that okay?
Yeah, for sure.
Okay, Faris, I don't know who's first. So. Yeah.
Hi, Kiana. So my question is actually about the inference time analysis. So did you do any inference time analysis, especially on the shorter tasks or the long horizon tasks? Since during inference time, you're using all the action history that has been done at a particular time. So I'm just assuming like for long horizon tasks, the later actions would be like pretty much slower than the early actions. So did you observe any such kind of patterns there?
So we did try an ablation that we changed the context window in the during the inference. So instead of giving all the history to the agent during inference, we kept it as the window size. And the performance drops drastically because it doesn't have access to the memory, and especially many of these rooms are quite big, so it was not able to have that memory of where it has been, and it would fail to successfully complete the task. But that's about it. I'm not sure what type of other value analysis you're looking for.
I mean, I just meant like the time it might take for subsequent actions in a like longer horizon task. Like when initially like you are doing initial action does not have like a lot of previous history. So first action might be faster, but when you have like already done 25 actions or 30 actions, so you are accumulating all that task history, that action history in your next inference for the action. So that might take more time. So like were there like
Takes more time as in like inference time?
Inference time, yes.
Oh, so we cache everything. That's why during inference time, it doesn't take as much. We had to do some tricks to make sure the inference time doesn't get very slow as we are increasing the episode length. Does that answer your question?
Yeah.
Okay.
We have two more, and then maybe we'll continue with the talk.
Sounds
Yeah.
good.
So there is a certain task that doesn't benefit from the perfect vision, which called room find or
The question is about the one task that doesn't benefit from ground truth vision,
Yeah.
right?
and
There was one bar like that in
yeah,
the.
why do you think that task doesn't really get any benefit from the perfect world semantics?
Yeah, so I should explain this better. When we say we have ground truth detection, we have ground truth detection for the target object. So in room visitation, which the task is to go to all of the room and say done, there is no detection provided. So that's why it doesn't benefit really. I believe you're talking about this one. So it doesn't benefit. Because there's no detection being passed to either of the orange or the blue plot.
So then what causes the difference in the bars? I guess just randomness?
So I think it's because basically the other tasks become easier and we have one model for all of these tasks. So it's one policy. So basically more of the capacity of the network goes towards the fetch, pickup, and object nav. And that's why we see a small drop in the room visitation.
We have two more, but let's cap it at, oh my God, okay. I don't know.
Yeah.
There's so many.
How did you define the training loss function? As my understanding, for the imitation learning, we should using the real world data set to define the loss function. And for you, how did you define your loss function for this one?
I don't know if you could hear. Question is, how did you?
So I heard the loss function that I can explain, but the next one was real loss function for real world.
Yes, right.
So we don't get any loss function during real because we don't do any real world adaptation. We only train in simulation, and in simulation, we basically have all these trajectories, and the only loss that we have is on the action. So the model provides all the action at each step, and our loss is basically a cross entropy because we have discretized action space, and the goal is to just predict the right action, and that's the only loss that we have during training.
Okay, thanks. I think we should let you continue, and then it's great that we have so many questions. Maybe we can take them a little later.
Sounds good. Okay, so great. We solved this great task, and we know that their community is also working on these tasks. So, what are we actually limited to a small subset of tasks by the design choices that we have made? So the current embodied AI community, similar to RT1, SayCan, it's like there is a big line of work that people are considering navigation and manipulation in isolation. Even though in our work, we weren't considering these in isolation and we had one end-to-end model, we still had a discretized action. And you could basically either move the agent, move the body of the agent, or move the arm. In the majority of work in the community, this is taken even to another extreme. Tasks are performed in two phases. So they first navigate to the object, then manipulate the object. So what is the problem with this? This approach is very restrictive. For certain robot designs, such as stretch robot, due to its constraint, this method might not even allow the agents to do some simple tasks such as opening the door. And the reason why I use this example of stretch robot is because the degree of freedom of the arm is very limited. So if it wants to open a door, it can't do navigation first and then manipulation. It has to consider these two together. And the other problem is that the community has been thinking about this in a discrete action space and only one type of activator at a time, either body or the arm. And the reason why we've been doing this is because for training the models and the setups that we've been using, transformers or doing like RL, end-to-end RL, we need that discretized actions. However, let's see if we want to wipe a table, if we want to open the door, if we want to close the curtain, we are doing all these tasks simultaneously. We are doing navigation. We are moving our body as we are moving our arm. As we are moving towards the door, we use the door. We bring our arm closer to the door handle to open the door. So not only having this separation makes some of the tasks impossible, but also it is not as efficient. So I go to the next component that I mentioned, that is modeling that supports complex tasks. So this is another work that one of my interns did, harmonic navigation and manipulation. And the first thing that we did was, instead of having discretized action space, we defined the action space as in a continuous form. And we worked with a variety of different tasks: opening door, wiping table, opening a fridge. And we tried to train a model in RL with reinforcement learning and simulation that transfers to the real world. The problem here was that RL in high dimension space is really hard. So there was a lot of tricks that we had to do to make it work. One of them was careful reward shaping. It was very critical to get the models off the ground. We need to use arm proprioceptive, which is basically inputting to the model where the arm is with respect to the agent body. Luckily, this is a sensor that we can get in the real world fairly cheap, because most of the robots have this API that provides you with arm proprioceptive. And then we did curriculum learning. Okay, so for the sake of time, let me just skip to the results. The results were Great. We were able to, again, only train these robots in simulation and evaluate them in the real world. And as you can see, the robot learns some interesting behavior. For example, opening the door and then opening the door using the handle and then pushing the door with the arm as it gets closer to finishing the task. The other one was cleaning tables. And these are the tasks that require a more, and the reason why we have these like big papers was the smaller there to put in weren't visible, so we had to make it more visible that the robot is performing the task. But these are tasks that in the robotics community, generally they're considered as harder, more complex tasks because first of all, they're long horizon. So you can't really succeed in these tasks using like by chance. There are many steps to them and they are more complex. So that was very interesting to see that we were able to get 70 to 80% success rate in the real world. And okay, so let's say that we have a model. Just one question, Adriana, how much time do I have?
I leave that to Alex. Let's see. At least I would say 10 minutes at least, and we have
Okay.
Yeah, about 10
Sounds
minutes maybe.
Sounds good. Sounds good. Okay. So let's say that we build all these models and we have these generally capable agents. Is this all we need? Is this me as a customer of a robot to have a robot in my home? Is this all I care about? That's not the case. As a customer, I don't care about a robot that generalizes to all houses or generalizes to any environment. I want it to be specialized to the scenarios and behaviors that I need, which is bringing me to the last point of my talk, adaptable policies. Okay, let's just make sure we normalize our definitions first. By generalization, we mean going to a variety of different environments, houses, layouts. And by specialization, I mean I want an agent that works perfectly in my house, different times of the day, with different clutters, with different configurations. So this is a video of my house. I have many unconventional items, such as hammock placed in the living room, and I have a very weird layout. So there is a high chance we cannot anticipate that a generalized AI agent will generalize to my house. But as a customer, I only care about the performance the robot in my room. That's why we used a recent API that was introduced, which just allows you to scan a house with your mobile phone, with an iPhone, and it gives you the layout of the house with the bounding box around the objects. And not all the objects, just big furniture, and it might miss some of them. So if you remember, I told you that we have this possibility of procedurally generate different environments. So we do this scan, we get the layout, and we procedurally generate different variations of that target environment. So let's say I'm a robot customer. Tomorrow there is a robot in my house. I take 10 minutes, and that's not an exaggeration, literally 10 minutes to scan the house. And then the model can be trained on different variations of my environment. They're not exact objects, they're not exact textures. It's just different variations that resemble my house. And this is a robot that goes around my house, and it's very efficient. It's not exploring as much because it knows the layout of the house, and it just goes to the target. So this is one way of specializing these agents to the environments that we want. So this was phone to proc. And the other definition of specialization is the specialized behavior. Depending on the situation, we expect our robots to exhibit specific behaviors. For example, if we have a robot that is vacuuming, we want them to be thorough and look at every single corner. If I'm asking the robot to bring me a glass of water, I want it to be efficient. I want it to just go directly to the mug and bring it to me. And if I have a kid that is asleep at night, I want the robot to be extra cautious to avoid collisions so that it doesn't make any noise to wake the baby up. Okay, so I want, even like for one user, I might have different needs during different times of the day. How can I have this specialized behavior? So desired behavior can come in a variety of different forms. I might want to demonstrate to the agent how to perform the task. For example, let's say I want the agent to always take a specific path when it's carrying a tray of food. I might want to use language instructions. For example, say, move safely and don't collide with objects or walls. I might want to use feedback. So in some scenarios, I might not even know what I want. But one thing that would help is look at multiple different trajectories and pick the ones that I prefer. And then the model on its own that recognizes which one is the target behavior that I want. So with that being said, we made this policy that we call promptable behavior, and it's a framework that adapts to diverse human preferences without pre-training the agent. So as I mentioned, we have 3 different variations that we input the desired behavior. One is using demonstration, one is using feedback between comparing different trajectories, and one is using language instruction. Then this preference gets represented by this vector that goes into the policy, and then that policy will have a different behavior depending on what was input to it. Okay, so one idea is behavior can be explained in the form of a reward. For example, let's say we have a reward with 3 objectives, first one motivating exploration, second one motivating path efficiency, and third one safety. Now, if we go back to the examples that I showed initially, if I want the robot to be safe, I want to put the highest weight on the reward for safety and lower weight on other rewards. If I wanted to be thorough while vacuuming, I can put a higher weight on exploration and lower weight on the other items. And if I wanted to be efficient, I can just put a higher weight on path efficiency. Okay, so now with that idea, we designed this network that has 2-stage approaches. So we have a multi-objective policy that, given a goal and the observation and a weight for that reward, it is able to generate actions and have a policy. So these weights, at the beginning of each episode, we randomize them, and the agent will see the reward based on the weights that we input to the model. So during training, I can see any different combination continue in continuous space, any different combinations of the different reward weights for each sub-reward. So during evaluation, I can just have a set of rewards, input that to the model, and it will change the behavior. Now, how we get the optimal rewards, optimal weights, I'm going to explain in 1 second. So just note that there is an assumption here, and the assumption is that the desired behavior is achievable by a combination of the rewards that we initially plan. This is a limitation for this work, but our hope is that down the line, we are able to, our next stage of this project actually is to have a learned reward instead of a reward that is manually designed. And instead of having the reward weights to be explicit, basically predict the weights of that reward network. Okay, so let's skip this to just to give you an idea, for example, if it's like time efficiency is more important, this is the result that we see, which is basically like being as efficient as possible. But if you want to explore more, but we still want to get to the to this computer like at the end, or the TV the agent will take a higher path or a bigger path. Okay, so how do we get the reward? We talked about 3 ways, right? One of them was human demonstration. I demonstrate a trajectory and I want the agent to repeat that trajectory, or have a trajectory that has the, not necessarily repeat that, but repeat that behavior. So for example, I show it the shortest path in one scenario and I want it to imitate that. So how we do this is we basically optimize the weights until the reward for that specific trajectory demonstration that we showed the agent to be, the probability of that trajectory becomes maximized. For the language instruction, we do in context chain of thought reasoning and in context learning and use an off-the-shelf LLM to get the reward base. And for incorporating the human preferences, we just use, we designed a trajectory comparison that we've provided some mathematical analysis for that as well. With that, I think I'm out of time. More results on all of these works can be found on our websites, and I'm here to answer any questions.
Okay, thank you. Okay, so we have, okay, I'm gonna take somebody else. There were a few questions in the back from before. I don't know if you guys answered.
It was a great idea and interesting project. I have a question relating to the transformer that you use to encode sequential context. So can we see? Yes. How did after applying transformer, we have a sequence of encoding vector? Yes. So how did you handle the sequential thing? Did you just concatenate them or flatten them together and then apply multi-layer perceptron over that, or something like?
So this is this, you see my mouse, right?
Yes.
Okay, so this component, this part, is calculated at each time step. So for each time step, I have this vector. And I can pass in the vectors for each of the time steps to this decoder. So that's how we are taking care of this sequence, like basically the temporal information. So all the sequence, every single step in the sequence is come as a form of a vector, which here we represent with these orange vectors. And this transformer can attend to all of the previous observations, previous embeddings.
Where the window size that you evaluate upon that come from?
Sorry, I didn't get the question.
You evaluate the performance of the model to see how the window size affect the results.
Yes,
where that window size come from?
Yes. Okay. So during training, because we can't fit all the sequence, we only train on a window. Like, for example, only in this sequence is just like 50, a window of 50 steps. And the agent will only have access to the last at most 50 steps. During evaluation, we have access to all of it. Now, this is true for all of the evaluations we have done, except that evaluation that I answered to one of your colleagues. But if we change the sequence length of how big during training, how big of a sequence we see, that's where the difference in the performance comes from. Now, we have trajectories that are just as big as this, like 50 episodes, 50 time steps, but we have trajectories that are much longer. So the window size determines basically how big of a chunk of this trajectory we are going to pass to our models.
So, and one more question, is this, the length of the window size would be wouldn't be like bottleneck for the model?
It will be a bottleneck. So if we go with like a window size of 5, we
Yes.
won't be able to train anything. But that's why we did this experiment to show that the higher the window size is, the better the performance.
It wouldn't be applicable on, for example, a long time data set, time series or video or something.
So there are a couple of different ways that you can go around this. One is, it is possible that just using a smaller window size, the agent learns enough information that is able to generalize to a longer horizon during evaluation. The other one is using GPUs with bigger capacity. So since we published this paper, we have tried sequence length up 200 and 400 as well. And but we had to use like 800 machines, multiple of them, in order to be able to fit it. But if, for example, let's say you're working at OpenAI with unlimited number of GPUs, then you can take this window size as big as you possibly can. The other way is learning a way, which is actually a work that we have in progress, learning a way to choose the frames that are the most important frames. So basically choosing the key frames. And that so far, this method has been more successful than actually choosing those key frames. But I'm sure there will be a method that outperforms the existing keyframe detection, and that would definitely help to have a longer memory and afford having a bigger memory.
Yes, I think the last one is so interesting. I think it will work for longer.
Yeah. Okay. Thank you.
Can I ask a quick question?
Yes. Go ahead.
So there was an expectation of, I think, implied assumption that the tasks are all doable. Is there something in future work where, that nobody say, well, there's like stuff in between me and the apple, I cannot get to the apple, no matter what I do?
Sorry, I am having a really hard time hearing.
The question is like, did you try tasks that are like not feasible, and what did the robot do in those, if you did? Which may be.
Oh, yes. We actually have this experiment of, we call it finding the duck experiment. So we chose a category of object that we know it doesn't exist in our scenes, and we just sent the agent to go find a duck to just evaluate the exploration capabilities. And yeah, it can explore the environments. And even for the task that the object does exist and it is feasible. So one thing that I'm a big believer is working against cherry picking. So that's why on our website, we released every single trajectory of our model on the test set, successful or unsuccessful. And it shows that when we say our model learns to explore, it's not limited to successful tasks or unsuccessful tasks. It's like general across the board.
Thank you.
Thank you. Other questions? We have maybe time for one or two more. Yes.
I have a question for trajectory and navigation. And as you said, you use a monocular RGB camera to do so. I think the robots also need to record the paths they have worked. So I assume maybe you need a visual odometry to do it. Did you use it?
To do what? To avoid the collision?
I mean to record the trajectory it has worked before.
Nope, nope. That's why everything is surprising. We don't have any visual odometry. We don't do any. It's basically pure because during the training episodes, it has seen the trajectories of the agents going around and never visiting one room twice. It learns that skill without any additional supervision or sensor.
Thank you.
Thank you. First,
Yeah, so I guess I have like a couple of short questions. So first is regarding in the specialization with retraining based on the demonstration. So do you find any relationship between the generalization and specialization in that category? Like a robot that generalizes better will be able to specialize better? Like, did you do any experiment for that, or is it not the case?
So the robot that can generalize better, it's just zero shot performs better on that special environment. But if you compare that method with a model that is fine-tuned, so generally we also don't train from scratch on these specialized environments. So we fine-tune that generalized model on this specific environment, and the results, I didn't show the results, did I? It works, it's like, it goes from average of 30% to 75%. So it was a big gap. There was a big gap between the generalized models and the specialized models.
Maybe I framed my question wrong. So my question was in comparison with two different generalized models, one with maybe lesser diverse data and the other with more diverse data. And do they have any comparisons when you apply the same retraining procedure with the same specialized data like this?
Oh, is there a correlation between the generalization of our backbone to the model? That's a good question. No, we don't have any studies on that. But that's a good question.
Okay, so there is one more thing. So the simulations that is there in the simulator, are they all US based, or do they have like diverse data from other countries too? Because I assume like at least for simple tasks like opening a door handle in the US might be at a particular place, but in other countries, there would be different kinds of door handles, and that too at different places over the door. So would it be able to specialize people situations?
Yeah, that's a very good question. So our simulation is not based on any specific environment and is procedurally generated. But the assets that we are using, they are sampled from this observer's asset, which even though, so in the observer's paper, we do have a plot that shows where these assets come from, like what is the origin of their creator. But the majority is in the US. We have some creators from from Europe. We have some creators from Asia. But to answer your question, I don't have this specific answer of like the diversity of the environments in whether they're more resembling a house in the US or somewhere else, because the assets and the layouts, they're just chosen randomly from this big pool of environments and asset library 2D objects.
okay.
So the objects can be created by people from all over the world, but whether they have like had this specific like mind in designing them, that's a different question.
Okay, I would say we're at time more or less. So let's thank Kiana again.
Yeah. Thank you for having me. It was very great seeing you all.
Thank you for the very exciting talk. You want to say hi? So my students are mostly dispersed.
I want to say hi.
Yes.
It was really cool. Really great work.
Thank you.
I actually had one question about the 100 houses to 10,000 houses. You showed two graphs like this, and there's like a 15%. What about 1,000, 2,000, or how is that curve? Is that like this? Is that like this? Did you try 200?
No, I think we tried 10 houses, 100 houses, 10,000 and 100,000.
Oh,
And
but
it
nothing in between.
starts slowing down between 100,000 and between 10,000 and 100,000. But we didn't do more granular than that. It's just a matter of compute. So that's the only reason why we didn't do it. Yeah. But I think it's like much going till 100. It was, we could see a very obvious curve that
Right.
we get
So, but
improvement.
it would be interesting to know if with 200, you already get 5%, and then with 300, you get 10%, and then it slows down, right? So instead of the big jump, because from
Yes.
100 to 10,000, it's 100-fold, right?
Yes, that's true.
But I really liked your talk. Thank you.
Thank you so much.
Thank you very much. Yeah, I guess we'll give you 15 minutes back unless you want to talk to Sina.
Okay.
Yeah, thanks. It was very, I think a lot of people enjoyed it, even ones who don't. I mean, most of us, I don't think any of us work on anything like that, but
No, I mean, I think I would say that the only part that was a little close was generalization. That
Sure, yeah.
you skipped.
Yeah.
I think it was very interesting to me that you could generalize the zero shot to a
Yeah.
real. But I think parts asked too. I think maybe one way that it's coming is because the backbones, the clip, and all of them are trained on real images. So
They are trained, yes.
and they're not, so they're pre-trained. You don't fine tune them.
Yeah,
So they have some understanding of how
for sure.
environment looks in the real world.
Yes, exactly.
And so when you were saying, we trained in simulation and then tested in real life. My house, when I have a Roomba, it's a pain in the butt because I have to take everything out of the floor so the Roomba doesn't get tangled, and it's very sanitized, right? Which I understand. It's the first steps, right? Or the 10th step and not the 1000th
And it doesn't have
step.
any vision. Those are only with,
Yeah, I know, but what if I, because I get to my house, I take my helmet and I put it on the floor, I take my shoes off, and then I live by myself, so I don't really care how messy it is. And so, if you had stuff on the floor, the robot probably wouldn't be able to navigate that well and would be hindered, right?
It depends. If there is a path, it can get around it, yes, it can. Actually, for our phone to proc, one of our experiments that we showed was how robust it is to clutter. So we would just add stuff on the ground to just basically, some of us in the team have kids, and they were like, I'm gonna make this look like how my house looks like when I go home. And we added clutter, and it was very robust to it. I think it's because during training, it sees a lot of different clutters on the ground, so it's actually robust to it.
So I think somebody should write a paper that's named Robust Robot, because it's a good alliteration. And second, I really like that, I don't know where you're from, but you say on the ground the same way that I do, because I don't really distinguish floor from ground. And my partner keeps saying, on the ground, what's the ground? What ground? Like, on the floor, ground.
okay, thank you very much.
Okay,
I guess
thank you.
Connect. Thanks. It was great meeting you.
Bye.
Bye. Have a good weekend.
You just press end.
Yep.
And then